Hi there and welcome to this video for Senior Physics on Electromagnetism and Electricity. In this video we're going to look at the capacitor charging and discharging, and also looking at how capacitors basically work when they're in two different types of circuits, such as series and parallel. Okay, so let's start off by looking at our charging and discharging of our capacitor. Now there are two main graphs that can be generated for a charging capacitor. That's a current and a voltage chart. Now below you can see we've got a current graph showing what's happening over time with respect to the current. Now remember, current is the flow of charge per second. Now basically what happens, if you imagine your capacitor like an empty wine barrel or a water barrel, basically what happens is as you pour the water in, the water fills up really quickly, and you get a huge amount of water that you can get in incredibly quickly. Now instead of water, obviously we've got charge, and that charge is electrons. However, what happens is as the water barrel begins to fill up, the amount of charge that we can get in at any moment of time actually begins to decrease. So it keeps decreasing and keeps decreasing and keeps decreasing until the water barrel is full. When the water barrel is full, we cannot get any more charge in. Well, it's exactly the same for a capacitor. As I said, instead of water, we've got charge. That charge is the negative electrons. So what's happening is on the negative plate, the electrons are being pushed by the battery, and when the plate is completely empty, there's a load of charge that can be pushed on that plate very easily. However, as the charge begins to build up over time, what happens is the negative electrons repel any electrons which are trying to get onto that plate. That slows down the flow of charge onto the plate. Because that's the charge, there's less charge going past a specific point per second, the current begins to slow down until eventually the push on the charge from the battery is equaled by the push of repulsion from the charges on the plate. The net movement from the battery to the plate is zero. So as a result, we get an inverse curve which is generated, as we can see on the graph here. So to recap, we get a massive flow of charge right at the beginning, but this decreases as time goes on due to the repulsion of the charges which are fixed on that plate until eventually it gets down to zero. So that looks at the current. What happens with the voltage? Well, the voltage is the opposite. And in this case, what happens is when we put the charge onto the plates, we increase the amount of energy that the charges have. Remember that the energy is generated due to the repulsion of electrons. So if we put more electrons on the plate, we get more repulsion. More repulsion means more energy, which means that we get a higher voltage. Remember, voltage is joules per coulomb. So as a result, we keep pushing and pushing and pushing and pushing all those electrons onto that plate until eventually you can't get any more in. Well, let's go back to our water barrel situation. Imagine the water barrel has got a small hole with a cork on at the bottom. So it's the hole down the bottom of the water barrel, and it's got a cork in it. As I start filling up with water, the pressure, and I'm going to relate pressure to energy, the amount of energy on the cork increases. This increases and increases as the water level gets higher and higher and higher. Once the water barrel is full, there is only a certain amount of energy that's going to be pushing on that cork. So the result is that pressure will stay at a finite amount, a certain amount, and it will plateau out. As a result, the water barrel can't be filled anymore, we can't get any more energy, the capacitor can't be filled anymore, so the capacitor can't have any more energy. So to recap, the voltage goes in the opposite direction. It starts off at zero and rapidly increases until it plateaus out to the point where there is no more charge that can be put on the plate. No more charge means no more repulsion. So that deals with charges. So let's have a look at what happens with respect to discharging a capacitor. Well, in this case, we both get the same curves for both voltages and current. Because what's happening, as soon as we discharge the capacitor, what the electrons want to do is to move from the negative plate to an area where there's a deficiency of charge, i.e. the positive plate flowing through a resistor. So what happens is right at the beginning, there's a huge flow of energy. and as a result there's a huge flow of charge onto that positive plate. Now this decreases with time until eventually the two sides of the plate become equal. Two sides of the plate become equal. On the negative plate there's less repulsion, which means there's less energy, which means the voltage drops down to zero. Also, because the charge is trying to flow to the positive plate, eventually that charge will be repelled by the positive plate as it gains more electrons, so the net charge will be zero. So as a result, we get our curves following that inverse curve down to equaling zero, and at that point the capacitor has been fully discharged. Okay, well I hope that makes sense to you. Again, you can use that scenario with the water barrel. Pull the plug on the cork out of the bottom of the water barrel, you get a massive flow of water coming out. That's our current right at the top. That will go to a trickle until eventually that water barrel is completely empty. Put your face by the plug. As you take the plug out, that pressure from the water coming out of the barrel is going to hit your face. It's going to be really, really hard, but as time goes on, it gets softer and softer. There's less energy which is going to be dissipated or pushed onto your face. So the capacitor works in exactly the same way. As I say, instead of water, you've got charges there. Okay, so let's look at what happens to capacitors in different circuits. Now we know we've got two types of circuits. We've got series circuits and we've got parallel circuits. We learned that when we looked at our resistance work. Now basically, if we've got a series, basically all the capacitors are put in one major loop. If we're in a parallel, they're put in branches. Now you can see we've got a series circuit here where I've got two batteries. The two batteries are then linked via a loop to two capacitors, C1 and C2. C1 and C2 will have a voltage, V1 and V2. And that voltage basically will mirror the amount of voltage which we've got from the battery. So what do we know about series circuits? Well, we know that the charge on each capacitor in this case is going to be the same if they're the same size capacitors. So you can see Q minus and Q positive. Now the Q positive actually doesn't exist. What's happening is in between, in that middle part, the electrons are moving from the left hand plate to the right hand plate, making capacitor 2 Q negative. As a result, that right hand plate on C1 becomes Q positive because it's a deficiency of charge. On the outside plates, what's happened is the battery has pushed all the electrons to the left hand plate of C1 and taken them from the right hand plate of C2. That's why you can see on the outside we've got Q negative and Q positive again. Now what's happened is the overall effect is that we get all these electrons put on these various plates. Now what else do we know about series circuits? We also know that if we put any component across a series circuit, their voltages, when they're added up, will equal the same as the voltage of the power source, or the V supply. So V will equal V1 plus V2. So obviously if I've got 6 volts from my power supply, I've got the same size capacitors. Each of my capacitors will have a voltage of 3 volts. It's split equally. Obviously if the capacitors are different sizes, then the amount of voltage will be proportionate to the size of the capacitor. So from that, what we need to be able to work out is how do we determine the total capacitance. Now we'll see when we look, if you look at the FET video which accompanies this post, that when we put our capacitors in series and we add more and more capacitors, the actual capacitance of the two together actually decreases. And as a result, we get an algorithm which you can see below in red, that the supply capacitance, or in series circuit, the total capacitance is going to be equal to the inverse of 1 over C1 plus 1 over C2. Now the key thing to remember when you look at these this algorithm is solve the right hand side first. So do 1 over C1 plus 1 over C2, get a fraction, and then top and tail the fraction, inverse it, and then that will give you what the total capacitance is for that circuit. Now that deals with series, so let's look at parallel. So here I've got a parallel circuit. You can see that I've got two capacitors. they're in a parallel, they're the same size capacitors, and we've got a voltage. Now basically the voltage across each capacitor is going to be the same. So as it flows through each branch, it's going to have the same amount of voltage. So again, if I've got 6 volts in my power supply, each of my capacitors will have 6 volts flowing through them. Now basically we know that the charges on each case are going to be split up. So the total charge coming out of the power supply will be split equally between the two capacitors. And that's similar to what we talked about with respect to current. Current splits up and changes as you go into parallel circuit. Now, to actually work out the total capacitance there, basically we work on the principle that the capacitance for a parallel circuit is C1 plus C2. So we add the two capacitances together. Okay, well I hope that makes sense. So let's put this into practice and have a look at a quick example. So here you can see I've got a circuit where I've got a 12 microfarad capacitor, and then that's linked to two capacitors in parallel, 4 microfarad and 2 microfarad. Now the way to solve this problem is to try and convert all of the capacitors into as though they're one big capacitor to find out the overall capacitance. So the way we do that is deal with the parallel first. So if I deal with the two in parallel, we know that in order to work out the total capacitance of capacitors in parallel, we add them together. So I add 4 microfarad plus 2 microfarad, and I end up with 6 microfarad. So that gives me a situation where I've got a 12 microfarad now joining with that combination of those two parallel capacitors, which equals 6 microfarads. So now I've got two capacitors in series. So what I do is then use my formula for series, which is 1 over C equals 1 over C1 plus 1 over C2. Substitute in my values, so I get 1 over 12 plus 1 over 6, which is the same as 3 over 12. Then I have to inverse it, so I get 12 divided by 3, which means that the overall circuit has an overall capacitance of 4 microfarads. Okay, well I hope you found that useful, and I hope you sort of understand the idea of discharging and charging capacitors and how we deal with capacitors in series and parallel circuits. Have a go at some of the exercises that I put up on this post with respect to the worksheets. They'll look at discharging and charging, and also series and parallel questions. There's also a video using FET to try and show you the idea of series and parallel circuits, and I've also put up a YouTube clip which shows capacitors charging and discharging. So thank you for watching, and I look forward to you joining me again.